This presentation looks at the tests used to determine which halide ion is present in a solution known to contain one of the halide ions. By the end of the presentation, you ought to know what substance is used for the test. You ought to know how to interpret the results of the tests, the different possibilities. You ought to be able to write ionic equations for the reactions involved in those tests. If you've already learnt about the solubility of the halogens, the elements, you'll know that they dissolve to a greater or lesser extent in polar or non-polar solvents and form solutions with some degree of colour. The halide ions, however, are different. They don't dissolve in non-polar solvents like cyclohexane. They only dissolve in water, and the solution that you'll get will be colourless. So they'll be part of a compound like lithium chloride or potassium bromide, and those substances, they're white solids and they dissolve in water to give colourless solutions. So you can see here a solution of potassium iodide. So it's got iodides present in solution. It's an aqueous solution, completely colourless. There's no point shaking with cyclohexane like we did for the halogens. Halide ions don't dissolve in non-polar solvents like cyclohexane. So how do we know which of the halide ions was present in this colourless solution if we weren't told? The answer is that we add another colourless solution called silver nitrate solution to our mystery solution where we're trying to identify the halide ions, and we'll get a visible result. What we'll see are different coloured precipitates. Now, if you haven't come across the word precipitate before, that simply means a solid that appears when two solutions are mixed. So on mixing the silver nitrate solution with the solution we're trying to identify the halide ion, it'll go cloudy as a solid forms. If you left it to settle, it'll settle to the bottom, and you'll get different colours depending on which halide ion is present. That's summarised in the table here, and you can see an image of some of the tests below. You need to memorise a certain amount of this detail. So you need to know that if chloride ions were present in the solution, when you add the silver nitrate solution, you'll get a white precipitate. What that precipitate is silver chloride, and that's got the formula AgCl. So on mixing silver nitrate solution with a solution, any solution containing chloride ions, we'll get a white precipitate of silver chloride, AgCl. And we'd always write that precipitate with a solid state symbol because it's a solid. That's the whole point about a precipitate. Going through the other halide ions, we get the same sort of thing going on, but a slightly different colour. So the bromide is described as cream, sort of off-white colour, and the precipitate here is due to silver bromide, the formula AgBr this time, also solid, it's a precipitate. And finally the iodide, yellow, due to the silver iodide precipitate, AgI, solid. If you look at the diagram, you might question whether there's a huge amount of difference between the chloride and the bromide, but if you do see them next to each other, the chloride is genuinely a sort of bright white precipitate, whereas the bromide is off-white, creamy colour, and the iodide is definitely yellow. What's going on here is simply that when you mix these solutions, the silver ions from the silver nitrate can't be in solution at the same time as halide ions. So where there's halide ions present in your test solution, they will join with the silver ions to clump together as an ionic lattice and form a solid which will settle out of the solution. We need to pause here just to get one thing very clear in our minds, which is that this idea of the silver nitrate test only applies to the halide ions, and people find it very easy to get confused here. So just make sure you've got this straight. The halogens, the elements, do not give precipitates with silver nitrate solution. So if you add silver nitrate to a solution containing potassium iodide, so with iodide ions, yes, you get the yellow precipitate of silver iodide solid. But if you add silver nitrate to a solution just containing iodine, the element, do you get the yellow precipitate? No, you don't. This is only for the halide ions, not for the element, the halogen. So silver nitrate and iodine, no precipitate. And the same applies for the other halogens. Silver nitrate and chlorine, no precipitate. Silver nitrate and bromine, no precipitate. So make sure you've got that firmly in your mind. As well as being able to interpret the results of these silver nitrate tests for halide ions, we all need to be able to describe the type of reaction involved and to write balanced equations to represent it. So the type of reaction is known as a precipitation reaction, simply a reaction that forms a precipitate, and that's a term you need to know. And these are normally represented using something called an ionic equation. That's a slightly specialized version of the balanced chemical equation. It's something that you need to be able to produce, and actually what we'll find is it's a much simpler way of representing the reaction than the traditional full balanced chemical equation. So let's unpack what we mean by an ionic equation for a chemical reaction, and we'll do it in the context of silver nitrate reacting with lithium chloride solution. We'll look at the reactants in turn and then the products and use that to build up this ionic equation. Start with the silver nitrate. Now, silver nitrate is an ionic compound, and the two ions involved, silver and nitrate, are ones that you need to have memorized. They're not ones that you can just look at the periodic table and know. The formula of silver nitrate is AgNO3. And when it goes into solution, and this is true for any ionic compound, you don't get AgNO3 particles in solution. What actually happens is that the ions in the lattice, the positive and negative ions, move apart from each other, and so you get a solution of positive ions and a solution of negative ions. So actually, we can think of a solution of silver nitrate as a solution of Ag+, silver ions, and NO3- nitrate ions. When it actually comes to the reaction then, the silver ions, they take part in the reaction. They're part of the formation of the precipitate. But the nitrate ions, what do? Well, they do nothing. They just stay in solution. And we have a special name for that in chemistry. We call them spectator ions. The name kind of makes sense. They're just there watching the show. They're spectators. We said we'd take the example of silver nitrate reacting with lithium chloride, so let's consider this other reactant now. Lithium chloride is another ionic compound. You ought to be able to work out its formula, and that'll just be LiCl. As I said before, when ionic compounds go into solution, the ions in the lattice separate. So a solution of lithium chloride can actually be thought of as a solution of lithium ions, Li+, and a solution of chloride ions, Li-. So what do these do in the reaction? Well, the lithium ions do absolutely nothing. They just stay in solution, and so they're spectator ions again. The chloride ions, now those are the ones that will be reacting with the silver ions to form the precipitate, and so they are a reactant in this reaction. When we react silver nitrate solution with lithium chloride solution, we'll get the white precipitate of solid silver chloride. And the formula of that, we should know by now, is AgCl. Now, this is not something we're going to think about as separate ions in solution, because it's not in solution, right? It's a precipitate. That's the whole point. So this is AgL solid. So if we think about the things that we said were reactants, the silver ion and the chloride ion, and now our product, we can write those as an equation. Ag+, the silver ions aqueous, react with Cl-, the chloride ions aqueous, to make solid silver chloride as the product. And this is what we know as an ionic equation. So an ionic equation is simply an equation that ignores any spectators, the things that just sit there in solution and are unchanged by the reaction. We took a fairly lengthy journey there to get from the reactants to the ionic equation, and the reality is actually we can take a big shortcut when it comes to writing ionic equations for precipitation reactions, and that's simply to work backwards from the precipitate. So imagine a scenario where you had a solution, you added silver nitrate, you got a yellow precipitate, and you think, aha, this is silver iodide, there must be iodide ions present. So we can write the product of the reaction, the precipitate, AgI solid, and then for the reactants we can just unpick what ions must have been present in solution to make that. And that is simply the silver ions, Ag plus, Aq, and the iodide ions, I minus, Aq. And we can do that for any of these silver halide precipitates. So if you get a cream precipitate, you think to yourself, silver bromide, there must have been bromide ions present, and that's AgBr solid. Unpack that, and we get Ag plus Aq and Br minus Aq as our reactants. And we've already shown for the silver chloride, Ag plus Aq reacts with Cl minus Aq. So the point to get here is, it doesn't matter what else was present in the solution with a halide ion. The top one could have been potassium iodide or lithium iodide or sodium iodide or anything iodide. When we add silver nitrate, it's just the iodide ion that reacts with a silver ion to make the solid silver iodide precipitate. The same principle applies to any precipitation reaction. There's nothing magical here about the silver halide precipitates. So imagine a precipitation reaction which produced a precipitate of iron 3 hydroxide Fe with 3 hydroxide ions as shown here in the formula. We can work backwards to an ionic equation for this. We just need to think what ions would have been present in solution that joined to form this precipitate. Now, this does require you to have remembered, as you should have done, that the hydroxide ion is OH minus, and so with 3 of them in the formula, the iron ion must have been Fe3+. So we can unpack this product to give Fe3+ Aq and 3 OH minus Aq as our reactants. Finally, here's a question to check your understanding. Write an ionic equation for the precipitate that would form when silver nitrate solution is added to magnesium chloride solution. And to be honest, you ought to be able to predict the colour of that precipitate as well. So hopefully you decided that this would be the ionic equation. It's absolutely no different to any other silver nitrate plus something containing chloride ions solution. Ag plus Aq plus Cl minus Aq makes AgCl solid. So if you want, you can just memorize these ionic equations for the silver halide precipitates because they'll be the same. It doesn't matter what other ions are present. And hopefully you remembered that would be a white precipitate.